Probably I'm the only person who is academic himself coming from university, but I'm well connected with you. I'm a University of New South Wales member. Also, I'm a mechanical engineer, purely. So here to share some exciting news and technology has been developed at the University of New South Wales. So there was a 16 million research income that I've managed to attract from government and industry. Most of them have been wasted, but a fraction of that money has turned into something that's seriously valuable. So I've been showing up in many of the news articles, including ABC News live show, who called me up like 2 hours before the live show, early in the morning. BBC News had a big hit that we start to get interest from pretty much everyone, investors, operators of the engines, engine developers, as well as general public. So I'd like to share the news, and to make my talk even more relevant, I'm even going to talk about some safety concerns utilizing hydrogen in your workplace. So hydrogen is something big now. It's a buzzword. Was big early 2000, if you remember, but then it has been quiet for a while. But then now we are kicking up again as a valuable commodity, particularly for Australia. So Australia has a great vision to utilize abundant solar and wind resources to convert some of the water that we can provide, seawater, convert that into hydrogen, and actually export it to countries where the energy demand is much higher than Australia, countries like China, Korea, and Japan. So we have a clear vision and plan for it. And the investment that's made to hydrogen production is just massive. So by just looking at the number figure, $315 billion, US billion dollar projected by 2030, the investment is increasing. And as I keep checking on the investment portfolio, the number is just going higher and higher, led by US as well as Germany, but Australian government is hopping on too. So if you're not really familiar with hydrogen as a new commodity, then you'll be surprised to hear colors of hydrogen. Hydrogen has no color. People try to flag the color in hydrogen. So our typical hydrogen is what's called gray hydrogen, that you just get hydrogen as a byproduct of your fossil fuel processing. Then if you have some carbon capture facility in your hydrogen production facility, then we start to call that as a blue hydrogen, rooting towards green hydrogen. When you say green, that means that the electricity generated from non-fossil based source, power source, energy source, and you use that to do water electrolysis to get hydrogen out of water. So that's green hydrogen. And there are a lot of feedstocks that I'll mention later on. But the use of it, hydrogen is nothing new. We don't have those in your household, but definitely it's been used in many processing for petroleum refining, glass purification, aerospace applications, in agriculture, making fertilizer. All these processes require hydrogen as one good element, needed element. So it has been around for long. So there is a very well-established safety standard around too. But then where do we get hydrogen is becoming a big question. So traditionally, like I mentioned earlier, it's been obtained as a byproduct of a fossil fuel processing. Then there has been gradual interest into producing hydrogen from other sources. Like one example is this coal mine, the coal power generation, coal mine and generate power plant that would be willing to convert some of their coal into hydrogen as a new commodity. The nuclear, where the electricity generation is continuing, that electricity can be used to generate hydrogen. Natural gas can be reformed, because if you remember, natural gas is CH4, so there are a lot of hydrogen molecules in it, so can extract hydrogen out of that CH4. On top of that, then we have some renewable sources. As I mentioned earlier, water electrolysis is one process to get hydrogen. That energy can be supplied from renewable electricity, or bio feedstock, where there is a low carbon, so it's a renewable, carbon neutral feedstock is provided to generate electricity. Then you use that for the generation of hydrogen. And we say that renewable hydrogen. So there's a mix of feedstock supplying hydrogen from greener sources, as well as traditional sources, increasing the hydrogen production overall, globally. Some exciting thing. I'm a mechanical engineer. Started my mechanical engineering study and continuing my career because of this. There are some exciting things about looking at cars running, generating power that's based on, combustion. That we burn petroleum or diesel in traditional cars, but now engine manufacturers are developing new kind of engines and vehicles utilizing those new kind of engines primarily for hydrogen as a carbon neutral fuel. So when there is a hydrogen supplied as green energy source, then there's a good use of a hydrogen in combustion engine. That's the theme here. Toyota is actually leading. This is the largest company in the world at the moment, automotive company in the world, surpassed Volkswagen a couple of years ago and actually widening the gap thanks to their great success in hybrid sales and actually profit made from hybrid sales. They are willing to put hydrogen car into the market. So first thing they did was converted their existing Toyota Corolla that into hydrogen engine, pure hydrogen engine, and put that onto one of the Japanese racetrack and demonstrated full race based on this new hydrogen car with a great performance. And there are a lot of development going on too from other areas, such as excavator, some heavy-duty truck manufacturers like Westport, working together with AVL and Scania, and also some retrofitting and conversion tech implemented by a European company called CMB Tech. Then heavy-duty engine manufacturers are joining into the party too. So Caterpillar is committed. They said that they're committed to develop and produce hydrogen engines, starting from the power generator, so genset. Cummins is actually leading in this space. They already announced the full development of these hydrogen engines for heavy-duty truck applications, carrying about 40 kilograms of hydrogen in one vehicle. That's a massive amount of energy carried. MAN is actually second largest in the world for power generator engine development, as well as power generator engines, as well as marine engines. They also have this hydrogen engine development plan and some demo project all completed successfully. So this range of engine developers are working on hydrogen engines. Then this is actually a chart categorizing all the hydrogen engine developed here and there. Nothing to be remembered for you, but important for information for me when I actually explain how each of these hydrogen engine is different to the other and how it is different to fuel cell system. That's the first application of hydrogen. It's been, so there are many questions about it, so we need a bit of a chart showing that. So let me just do one quick example here. So when you hear about Cummins heavy-duty truck hydrogen engine, then it is not fuel cell, but combustion engine. So we go left. And when you hear Cummins heavy-duty diesel engine, that's spark ignition engine. It's not diesel engine anymore. They converted their diesel architecture into petrol architecture and utilizing it as spark ignition engine, just like a natural gas engine that they developed before. So we go on the left. And then Cummins spark ignition engine would do either port injection or direct injection, depending on the generation of engine that they're generating. What they're talking about now is primarily port injection. So you supply hydrogen into the intake manifold and spark ignite it. Then the limitation there is spark ignition engine, mechanical engineers, has a lower compression ratio. So when piston cylinder is compressing, the volume change ratio is lower. That is translated into lower thermal efficiency. So your engine is naturally lower efficiency. That's why you are using a diesel engine in your workplace, higher torque and higher efficiency operation. So fundamentally, the efficiency is limited. Then the question is raised, then, is there any better way of using hydrogen in your existing engine or a new kind of engine that can give you better efficiency? So there are a lot of questions raised about it and development going on. And in a passenger car side, manufacturers like part manufacturers like a Bosch or BorgWarner, they are working on low pressure direct injection system, meaning that hydrogen gases are injected into the cylinder in a pressure that's higher than the typical port injection engine pressure, but much lower than diesel operation. Typical diesel engines that you're using are hitting now 3,000 bar of injection pressure. By the time the fuel is going into the cylinder, it's hitting about 3,000 bars, so 3,000 times of this atmospheric pressure. The first generation hydrogen injectors made by Bosch or BorgWarner, they are going at about 50 bar maximum, so 50 bar over pressure. That can give you nice distribution of hydrogen gas jet. And there are some optical diagnostic techniques that can visualize this invisible hydrogen, particularly Sheridan imaging technique utilized by Bosch. That's showing how hydrogen distribution could be different depending on the mounting position of a fuel injector. It was shown in this example. BorgWarner is going deeper into that development. They now have injector that doesn't have any holes, but has a pintle. So it has a slit of opening area where the hydrogen sealing can be much better than the typical hole type injector. And they're supplying the information about that through their computational simulation as well as its gas jet visualization. On heavier duty application, it doesn't actually go into the scale of earth moving equipment they're working on that you guys are using at the moment, but still it's a heavy duty applications for trucks and some marine applications as well, small marine engines. The most advanced technologies for this hydrogen utilization on that space is that you either do hydrogen pre-chamber ignition, meaning that hydrogen is supplied as a main fuel, but then you have a little chamber that includes a spark plug in it. So you make a baby flame first using hydrogen through that spark ignition, and that reacting jet, the flame is coming out directly into the cylinder and causing that two-stage ignition, pre-chamber type ignition system. It is a great controllability it has, so robust ignition is possible using that setting. And Mali and Liebherr, that Swiss company, are commercializing that technology at the moment. In Germany, L'Orange it sounds French, but it's actually a Stuttgart-based German company. L'Orange has developed the injection system that can do both diesel and hydrogen injection in a single injector, integrated system. And they've demonstrated great flame development and the combustion of this hydrogen due to the sip of fuel, diesel fuel going in. It's like a diesel pilot fuel is generating little flame, and it's causing the reaction of a main fuel, hydrogen jet. So it's a hydrogen jet ignition and reaction that is shown as an example. Okay, so you've heard about Germans working on it, Japanese working on it, American companies are working on it and all, but how about Australia? So we've looked into many options to burn hydrogen better, and what's the missing element there, and we found this. What if we have two separate injectors? So you have existing diesel injector untouched in your engine. Typically, it's a centrally mounted right into the cylinder, injecting multiple jets into the cylinder, creating a symmetric form of a diesel jet. On top of that, then we can add a hydrogen injector so that we can have a full control of that hydrogen jet. And that's been studied in the lab facility. We are specialists in visualizing things and taking high-speed images and laser-based images as well. So we've looked into how hydrogen jet, even before it burns, is generated, and saw some interesting things like a barrel shock generation from the hydrogen jet injected at high pressure, like 200 bar. And then we also look into how the burning process itself is happening, and then realize that the yellow area shown on that left side to you, diesel jet, is actually causing the initial reaction, and the green area where the hydrogen reaction starts is catching up a fire around that jet in a nicely controlled manner. And that high-speed imaging shown over there gets you an idea about how that yellow-colored diesel jet is trailing the hydrogen jet green area and causing the reaction zone in a well-controlled manner. So we enjoyed that great controllability of hydrogen reaction through the control of diesel injection. So for operator's perspective, it is the same engine. These diesel injectors are still there. Someone showed up and gave you the additional hydrogen injector. The control is all done automatically. And then diesel injection timing control that you would do is the only thing that you will control the overall combustion, as in any typical diesel engine. So great usability of that concept, proven in a lab facility. But then we didn't stop there. We moved further, that we converted one of the existing diesel engines, initially small engine, only 83 millimeter bore, so half a liter per cylinder, small engine used for SUVs and ute and passenger cars, that we converted it with the same concept, untouched diesel engine only with the additional hydrogen injector added. We put the hydrogen in and control the diesel and hydrogen injection timing, amount of hydrogen going in by energy, and amount of energy supplied by diesel flame, all fully controlled, and we optimize the engine operation. And the performance charts showing there is actually confirming the excellent performance of this hydrogen diesel hybrid engine. So hydrogen jet ignited by diesel flame approach here, that we see the efficiency it is hitting. It's indicated efficiency of 57% maximum. And then it's actually a beater even to the fuel cell system, which hits about 53% indicated efficiency. Diesel operation is looking at about 50% efficiency, so we're actually winning even against the baseline diesel operation. Then we also looked at how much of CO2 reduction that we can achieve out of this operation. By supplying about 90% of the energy from hydrogen, then we could achieve over 80% CO2 reduction immediate. There was a big factor for us that, okay, here is an existing diesel engine operating just like a diesel engine with only additional hydrogen, that we can achieve over 80% CO2 reduction immediately by just making a small conversion into that engine. Then if you're really familiar with the engine technology, the first question they will raise would be about, how about NOx? So NO, the air comprises nitrogen and oxygen. And unfortunately, wherever there's a high temperature above 1400 Kelvin, this hydrogen and nitrogen, they breaks down and then meet together, form NO, nitrogen oxide, then settle down as a NO2. When you see much of NO2 in the atmosphere, then it's forming smoke, and it's becoming source of fine particles, and it's also your greenhouse gas emissions. So it's strictly regulated. Anywhere there's a combustion, even if it's a non-carbon-based hydrogen fuel, it's unavoidable. So the question is raised, okay, great combustion engine, how about NOx? The NOx is controlled by we having that diesel injection timing control intact, untouched. So through that hydrogen mixture making, fully controlled by us, and diesel injection timing and amount of diesel going in, fully controlled by us, we could manage the NOx just pretty much at the same level as the baseline diesel engine. So if you operate your engine with roughly about 20% higher efficiency, 80% CO2 reduction, the same level of NOx, and this is a big winner. Then how about compared to other technologies? It sounds exciting. University did a great job. There are many commercialized technologies around utilizing hydrogen. The first one you will hear would be fuel cell vehicles. There are many actually energy projects going on to implement fuel cell vehicles on the road or in a controlled environment and all. Absolutely fantastic, zero CO2 emissions. Hydrogen utilization is amazing, but the demand for the hydrogen purity is too high, which means the hydrogen production cost is too high, and the cell production for that fuel cell production cost is too high. So it will take some decades until fuel cell system can become practical and affordable at the same time. Hydrogen spark ignition engine, as I briefly mentioned earlier, for the Cummins engine, fundamentally it's running at lower efficiency than diesel architecture. How about then putting just hydrogen into the intake port? The simple implementation, don't even need to touch the engine, just intake manifold conversion or the port conversion with hydrogen in a diesel engine. That is limited at about 30% of hydrogen utilization by energy, simply because you're putting hydrogen too early. It's making too well mixed mixture. staying for too long in the intake manifold inside the cylinder and losing all the efficiency. Even if you seal it nicely, higher hydrogen fraction with that nicely mixed condition, unfortunately, is causing the troublesome knocking condition. And in this hydrogen knocking condition, that's engine damaging condition. So one big knock is not just a small knocking and pre-ignition, leaving some marks on the cylinder head or piston top, but it's actually engine damaging knocking that you can't really handle. So our hydrogen diesel hybrid technology based on this dual direct injection is controlling the mixture stratification of the hydrogen. So it's not fully pre-mixed, but it's causing the mixture that somewhere there's a hydrogen is mixed with the air well, and somewhere it is still going through the mixing process. Somewhere you have an enriched hydrogen relative to oxygen that is fully controlled by the injection control that we can do from two separate direct injectors. That's the end of the talk actually for most academics, but then as we are living in a world where academia cannot just stay as an academia, but have to reach out and do better socialization with the community and make a real impact to the economy as well as society. So we are really encouraged to bring this into the real world. Instead of waiting for the original engine manufacturers commercializing this in 5 or 10 years at a time, small startup companies based on innovative university culture can actually make a big difference. So we've moved ahead for that and came up with nice deals. Like there is a great initiative of implementing this new hydrogen diesel hybrid technology in the airport baggage tractor, very close to us here. Another pilot and demo project that we're working on is based on the Sydney Port, where we have a power genset, diesel power genset, power generator can be converted into our hydrogen diesel operation to demonstrate its full capability of running in a real site, in a real environment with actually people who manage these diesel power generators. If they can provide a training, if this can be accommodated in a real site with no drama. That's what we are actually currently demonstrating. And finally, thanks to Rio Tinto, who raised their hand to join in University Trailblazer program through the Department of Education, we've secured a significant amount of budget for the further development of this technology. We call this as a scale-up, major scale-up project that can be scaled up so that can be relevant to Australian mining. So we're looking at large-scale Caterpillar dozer as a first application. And towards that, even if it's proven in a half-liter engine or 1-liter engine, that's a single cylinder, 1 liter per cylinder engine, heavy duty, we have a long way to go for the further development of this technology in terms of the scaled-up application to this large-scale earth-moving equipment applications. So working on it, and I think in about 3 years, you will hear it's a major hydrogen diesel hybrid engines can be shown up in your work site. But before then, we'll hear it from other applications like power generators. So the startup company that I mentioned is named as a DECARIS. It's an acronym for Decarbonized Internal Combustion Engine. So myself as a co-founder and CTO, and I brought back my UNSW graduate, former student, back into the game that he had an ample experience back in the UK at Ricardo initially, and then joined in Cox Powertrain when it was only 5-member company, and then it has grown into a 150 employee company servicing all the new generation of engine to globally. So we're going to repeat the same thing. The business would look like that. You are approached by us pretty much, and we go to your site, take out one of the cylinder head, that's the only component that we need, back into our workshop, then change that by adding the hydrogen injector, amply developed, doing some remapping of ECU, and do the performance test in our dynamometer setting, and then bring it back to your work site and run it. That's pretty much a turnkey type service that we are actually developing as a business. If you're interested in investment, please come and talk to me. But then safety. my own experience. So when you're in university, it's very challenging to be super innovative when you're thinking about safety concerns. And of course, when you're saying that, hey guys, I'm going to bring hydrogen into my lab, then there are a lot of people who are saying no immediately. And I checked what's actually needed to be able to work with hydrogen in my laboratory. And it turned out that there is actually a standardized process. There are many experts, specialists, as much as I can afford it. Not much hassle. It's not that you have to create your own standards or have to talk to all these committee members to have a new set of standards. Instead, you can just follow the standards already provided through the consultation with the experts in the safety and inspection. So we talked to them and realized what's needed is just a small amount of funding for added ventilation within the lab. Not even forced ventilation, but passive ventilation needed. Did all the calculation. Lucky that I had have a spacious lab, so wasn't really concerned about the volume of air versus hydrogen that we're using. With that all in mind, the safety implementation has been quite straightforward. It is because it's not non-toxic gas, thanks to that. Just an example, if we were going to bring in ammonia to the lab, it will be a completely different story. So we would worry much more about the toxicity of this gas that we're using than it's being fire hazard. But for me, that's really important. The problem here is that hydrogen is extremely hard to detect. It's too small. It's only H2, so smallest molecule on Earth. So can't really deal with it without having proper sealing or control of or a regular checkup of any leak, potential leak, and even the predictive checking of the leak sources around. And it doesn't have any smell and no color. So the detection of hydrogen is becoming a real deal. And being small, as I mentioned earlier, is too hard to seal in many ways. And embrittlement is something that you might heard from somewhere, that any typical just carbon metal will become cracking easily by having hydrogen stored for too long. So stainless steel is the first material that you can use, or carbon fiber, costly carbon fiber to store a lot of energy in it. So most transportation applications that we're looking at, like Cummins diesel engine that I mentioned earlier, is based on those costly carbon fiber-based storage tanks, 5 of them carrying 40 kilograms in total. But in your workplace, most likely you will see this compressed gas, red colored, so visible. It's rated for fire hazard, so it has to be treated properly for that. The reason behind it is fundamentally hydrogen require extremely low amount of energy to ignite. And at the same time, there's a concept of flammability, how much hydrogen is needed to set a fire with respect to available air here. So you gotta make super extremely diluted hydrogen to be able to avoid any flame. So that's like an order of magnitude difference. So if you had this amount of gasoline or petrol, diesel, then it would set a fire at a certain condition. If you assume that, then hydrogen would require 10 times more, 20 times more air to avoid that, to make it diluted so that the cause of reaction wouldn't happen. And it's so sensitive to even like a little spark can cause fire and all, so it's a major safety concern for that. But like I said, it's not new that there's a standard being revised constantly. So Australia has this hydrogen standards, ME 093, well established, reflecting all the ISO and IEC standards, global standards. So we're not behind at all. We are actually going with the same pace as the global movement on the hydrogen safety management. Just make sure that we use material that doesn't cause any hydrogen embrittlement. Sealing should be taken carefully, more careful than some other gas resources we're using, like natural gas. Ignition source should be careful again, that if you were fine to have some sparking room light for nitrogen, methane gas or natural gas environment, just acceptable, but then for hydrogen, that's not acceptable. So there should be more best practice that needs to be implemented. Okay,
just to sum up, so hydrogen is a big thing. It will play a key role for our decarbonized future. No question about it. There will be a lot of hydrogen engines coming into our real life, from passenger cars, heavy-duty trucks, agricultural, construction equipment, and in the end, even earth-moving equipment that you're using. UNSW has developed this exciting new technology, so we'll be part of it, part of that big picture, by implementing this hydrogen diesel hybrid engine in real-world setting. Okay, we'll keep hearing news from us about the initial demo project and the growth of the company, startup company that I mentioned earlier, for a larger scale. Then hydrogen is a safety hazard. It has serious fire concerns around, so care should be taken to control it better. But there is a standard and procedures well in place, and it's being implemented very well. So nothing to worry about, just should be taken care of better. Thank you.